In the near future, I will be assuming new responsibilities as director of the Dickinson Research Extension Center, so my phone number will change, but my email will still be the same. If you have any sort of soil questions, I'd love to help you out with that. Okay, so soybeans, like any other crop, they require a number of different nutrients. Nitrogen, phosphorus, and potassium is what we really are concerned about with soybeans, and that's where we're likely to see a response. We'll talk about nitrogen and inoculation in a little bit. They certainly need some sulfur, calcium, magnesium, and copper. Magnesium, zinc, boron, chloride, molybdenum, and nickel, but all the research projects that we've conducted so far would indicate that our soils meet the requirements for yield. Now, iron in the yellow there, that's a little different deal, and we will talk about iron chlorosis and some management options, as well as testing that down the road. So when it comes to soybeans, we're limited with two big things. One is we're North Dakota, and we have winter and road construction season, but we also have water has a tendency to be a limiting factor. And so when we look back at Liebig's law of the minimum, some research in North Dakota by Botter and Ennen suggests that soybeans typically need about 17 inches of moisture. Well, with western North Dakota, so areas west of Highway 83, we're probably less than that in most years. And then it's not only the amount of moisture, but the timeliness of that. And we know that we need good, sufficient rains once we're in that reproductive stage. And that's generally during August when things have a tendency to dry out. So inoculation, we're talking about the nodules on the plant, these little white things. Those are bacteria, Brady, Rhizobia, japonicum. And it's important to know what that species is because they are specific for soybeans. So inoculation for field peas, that's a different species and won't form that symbiotic relationship with the soybeans. So soybeans, once that soil nitrogen is depleted, they send out these signals and the bacteria migrate towards the roots. They can travel a little bit. Under dry conditions, they can't really travel much. But they infect the soybean and they form the symbiotic relationship where they get some sucrose from the plant, but then they give the soybean nitrogen. And this is pretty intensive on the soybean or taxing on the soybean. In order to get some nitrogen, it takes about 10 pounds of carbohydrates in order for that nodule to produce 1 pound of nitrogen. So that's where there's a lot of interest in side dressing nitrogen because of that. But usually when you start looking at most of the research, if you have properly nodulated soybeans, they will yield just as well as soybeans that would have some nitrogen. So when you're looking at your nodules, there's a couple things to look for. One is you want to have a little bit of a pink look to them, and that's because of a hemoglobin compound. And our blood has hemoglobin in it, and that holds on to oxygen. So in order for these bacteria to fix nitrogen, they need to have an oxygen-free environment. And that's why when you see a little bit of pink, they're properly nodulating and fixing that nitrogen, converting that nitrogen gas into ammonium-type compounds. Now also, if you're looking at the nodules, give them a pinch, and there should be a little bit of a sweet smell. So that indicates that they are getting sufficient amounts of sugar from the plant. So question. So this is some research out of the Carrington Research Extension Center. On the far left, we have our site years. In the red, we have soybean history. And then in the red over here, more so in the middle, we have the yield with inoculation and without inoculation. And so if we look at 2003, there was no soybean history. And without inoculation, it yielded about 33 bushel. With inoculation, the yield did increase quite a bit, up to about 39 bushel. So there was a 6 bushel bump. Now, when we go down the years, let's take 2005, for example, there was a soybean history, meaning there were soybeans within the past 4 years or so of this crop. And when we look at the yield without inoculation, 39.6, and the yield with inoculation was 39.6 bushels. And so we see similar trends across all sorts of different studies with when you've had soybeans within the past 4 years, you're probably not going to see a response from the inoculation. But then a question arises, how many nodules is sufficient on a plant? So this is some work done by Carrington where they looked at nodules per plant, which is on the x-axis, and the yield in bushels per acre on the y-axis. And we can see with only a handful of nodules, so 5, maybe 10 nodules, they did measure the highest yield. So it doesn't take many nodules in order to have adequate yields. But if you're looking at virgin soybean ground, we do recommend inoculating those soybeans. And by double inoculating, we don't mean twice the rate of a granular or twice the rate of a liquid inoculum. We recommend 2 different sources of inoculum. So this is some work conducted by Shana Forrester at the Research Center in Minot. On our y-axis, we have the yield. X-axis, we have no treatment first at 22 bushel. With the liquid, we increased our yield to 29 bushels. With both inoculum, the liquid and the granular, it was similar to the liquid, but was definitely better than the granular. So double inoculate your soybeans if it's the first time that field has had soybeans. Now, some other work has been done to see, well, what happens if we put inoculum down the previous year? So Dr. Jay Goose and Pat Carr over in Dickinson, they looked at putting inoculum down with wheat and what its influence was on soybeans the subsequent year. So the picture on the left shows inoculum just with placed with the seed, and the picture on the right, I apologize for the graininess of these pictures, but you can make out there's still a number of nodules on the right-hand side, and so this was just wheat as the previous crop. So they looked at inoculating with wheat plus the year that they planted the soybeans, and they did see a little bit of a bump in the number of nodules per plant. But when you look at seed placed during when you plant versus the previous crop that was inoculated, the numbers seem to be the same. Now they never reported yields in that report, but there was an interesting difference with or similarity with the number of nodules per plant with that wheat versus the year of that soybean that was inoculated. So if you've had soybeans within the past 4 years and they had some nodules on it, so it doesn't take many nodules like I previously said, you're likely not to see a response from inoculating that year you plant the soybeans. We have different years after a soybean crop, and over here is showing how many cells of bradyrhizobium there are per gram of soil. So immediately after soybeans, there was 19,000. 2 years later, it decreased significantly to 3,700. 3 years and 4 years out, they were pretty close at a little over 2,000 cells per gram of soil. If we went out to 5 years, it would decrease slightly again. The decline year after year has a tendency to asymptote out and no longer decrease. So yeah, our data shows for 4 years or so since your previous soybean crop, you're probably not going to see a response from that inoculation. So then another thing with soybeans is they fix their nitrogen, and there is a soybean nitrogen credit the subsequent year. We call it a credit because it doesn't show up on that soil test. What happens, or I think a common misconception out there, is that the nitrogen for your subsequent crop, and we recommend 40 pounds of nitrogen per acre, that nitrogen is coming from the soybean, and that actually isn't true. When you start doing mass balances of how much nitrogen is fixed by the nodules versus biomass produced and what is hauled out in the grain, it's actually in a deficit. So the plants are still getting a lot of nitrogen from mineralization when that soybean's growing. But really what's happening is the soybeans create an environment that's conducive to mineralization. And so it encourages a bunch of the soil organic matter to mineralize and become nitrogen for your crop after soybeans. If we start looking at organic matters, they have a tendency to decrease following soybeans, and that's coming from that mineralization. So then another common question we get are, what about rescue nitrogen applications? Where we find a response with rescue applications, and where it's probably only profitable, is when there's no nodulation and when you time that nitrogen application at the R3 growth stage. So this is some work that was conducted by Greg Endries and others at the Carrington Research Extension Center. They had 100 pounds of nitrogen from urea, 100 pounds of nitrogen from UAN, 50 pounds of nitrogen from UAN, and 50 pounds of nitrogen from urea. And then there was also the untreated check. So at 50 pounds of nitrogen, there was a yield bump. At 100 pounds of nitrogen, there was a greater bump yet. And it's really not so much the source, but it's just the amount of nitrogen that you need to be concerned about. And so John Hurd, another soil scientist up in Manitoba, has observed similar responses as well. If you have no nodules, or you had some issues with maybe your inoculum applicator was plugged up or something, some rescue nitrogen in that later reproductive stage might be beneficial. So that's nitrogen in a nutshell. We're going to talk about phosphorus. And we recently updated our soybean fertility guidelines. And if you look on these guidelines, if your soil test is 8 parts per million or greater, we no longer recommend phosphorus. And that's just because it's unlikely to see a response from the phosphorus in the soybeans. Now, if you put soybeans down year after year and don't put phosphorus down, your soil tests, they could deplete. So keep that in mind. But Calra and Soper up in Manitoba back in the late 60s, they did some work where they looked at isotope phosphorus fertilizer. And what that does is that allows us to determine where the phosphorus in the plant is coming from. So this is a special isotope in the fertilizer, and you measure the phosphorus in the plant. And if it has more isotope fertilizer or phosphorus in it, then that would indicate that most of the phosphorus in the plant is coming from the fertilizer. If it didn't have a good amount of the isotope phosphorus in it, then that would indicate that the phosphorus came from the soil. And so looking at that, Calra and Soper found that soybeans are one of our most efficient soil phosphorus uptake crops that we actually grow. Maybe not as great as flax, but certainly a lot better than our small grains and corn and a number of other crops. In 2016, Bardella was an MS student in Manitoba. They had 28 site years of phosphorus rates on soybeans, and they were low phosphorus tests. And only one site out of the 28 site years did they see a positive response from the use of phosphorus fertilizers. And in order to have that response, it took 90 pounds of P2O5. So you're looking at somewhere around 180 pounds of MAP to see a yield response. So just keep in mind, soybeans don't really need that much phosphorus, but it could influence your Olsen phosphorus test over time. Now, a common thing that we see from state to state as we look at different fertilizer research projects is that soybeans prefer their phosphorus broadcasted versus banded. Now, when we look at our small grains or corn, we know we can cut our phosphorus application rates down quite a bit, but still maintain similar yields. But soybeans, when you look at the same amount of phosphorus, they tend to yield a little bit better with broadcast. But if you're a no-tiller, if your soil test calls for phosphorus and you're banding, I would want to put it down in the band versus not putting any phosphorus out. So on the far left column, we have the amount of phosphorus, 0, 20, 40, 60, and 80 pounds per acre. And we see with the broadcast, when we look at like 40 pounds of P2O5 our yield was 41 bushels. With the 2x2 band, the yield was a little bit less at 36 bushels. At 60 pounds of broadcasted phosphorus, the yield was 44 bushels versus 39 bushels with the 2x2 band. So there does tend to be a little bit of a yield advantage with broadcasting phosphorus versus banding the phosphorus. So then in-furrow liquid fertilizer, phosphorus fertilizer can influence things as well. And we've been doing work on that. I'd like to highlight a study out of the Carrington Research Extension Center where we have our application method of the check. 4 gallons of, I believe this was 1034O in a 2x2 band. In-furrow, 4 gallons of 1034O, and also in-furrow 8 gallons of 1034O. And as they increased the amount of in-furrow fertilizer, the stand counts went down quite a bit. And if you remember from Greg Endry's presentation earlier, about 150,000 plants per acre seems to be the sweet spot for soybean production. And consequently, our yield went down, but also that influenced our yield. So the check yielded about 33 bushels. That 2x2 band of the 4 gallons yielded about 34 bushels. But then when we get to the in-furrow rate of 4 gallons, we have a yield decrease and an even greater yield decrease at 8 gallons per acre. So that's phosphorus in a nutshell. So potassium, we've adjusted our potassium recommendations based on your location. And so, 5 or 6 years ago, John Brecker, who's now with AgVice, was a grad student of Dr. Franzen's, and they were evaluating different potassium tests. And what they found is if they account for the clay mineralogy of the soil, that had the greatest influence on accuracy of the potassium test. And so we have a number of different types of clay in North Dakota. We have schmecktype, which that is the type of clay that expands and contracts when it's wet. If you go to Fargo in the summer when it's really dry and you have those big cracks in the soil, that's because the clays have shrunk. But when it's wet, they expand, so you don't see those big cracks. And so the schmecktype, it's kind of like a bologna sandwich. You have a layer of bread, and then a hunk of bologna, and then another hunk of bread, and then you stack all of these sandwiches on top of each other, and there's space for the water to get between each sandwich so it would expand and contract. Now, when schmectitic clays get dry, they shrink, but then they can also temporarily retain the potassium. So you might have applied potassium appropriately, but you may still see some potassium deficiencies. And that's because the potassium is there, it just can't enter the soil solution because it's trapped within the clay. Now we have this other type of clay called illite, and it's like schmecktype where it's that bologna sandwich, but between each sandwich we have potassium. And so the illite clay soils, even when they get dry, they aren't as likely to temporarily retain the potassium. So the potassium is still more so available to the plant under those conditions. So after they found this out, Dr. Franzen sent a bunch of us out throughout the state, and we collected 2 to 3 samples in each county based on soil types, or major soil types within that county, and we had them analyzed for the amount of schmecktype and illite clays. And so these gray areas that you see, like up in Morton County, or up here in Divide in northern Williams County, or in the Red River Valley, those are areas where the schmecktype to illite ratio is greater than 3.5, and that's kind of the golden number where we adjust our thresholds. So with these thresholds, we change the amount of potassium that you would apply. So up here we have very low, the VL, L would be low, M is medium, H is high, VH is very high, and we have these different levels or ranges that you get back on your soil potassium test. Now, when we look at this bottom column, that's telling us how much potassium we should be applying. And really how to interpret this is, let's say we get a soil test back that says we have 130 parts per million of potassium. Well, if you're one of those illite areas, so that would be an area here where it's white, we'd recommend 30 pounds of potassium. But if you're in one of those schmectinic areas, excuse me a second. So if you're one of those schmectinic areas like Morton County, but you have that soil test comes back as 130 parts per million, we'd recommend 60 pounds of K2O in those fields. And again, that comes back to how the clays have the ability to prevent nutrient uptake within the soils. So iron deficiency chlorosis, or IDC, is another big issue that we see in North Dakota. When dealing with this, the first thing to look at on your soil test is the pH. If it's less than 7, you don't need to worry about IDC. If it's greater than 7, you need to test for the calcium carbonate equivalence of that soil, and we call that CCE. If that test comes back and it's less than 2.5%, you're at low risk, so you shouldn't have to worry about IDC. But if that number is between 2.5% to 5%, you should be making some management practice, putting some management practices or implement some management practices to account for the IDC. And if it's 5% or better, you definitely need to. Now, the best way to manage for IDC is to plant a tolerant variety. The second best way to manage IDC is plant a tolerant variety. And the third best way to manage for IDC is plant a tolerant variety. Because the variety can have such a high influence on how well that plant will perform under those conditions. Now, if you look at the North Dakota soybean variety trials, every year, Dr. Ted Helms evaluates just about every cultivar that's tested within NDSU, and they're all put in the same field, so they're all on a level playing field to compare variety A to variety B to variety G to each other. Now, even if you plant a tolerant variety, you still may see some IDC, and that's where iron chelate fertilizers can come into play. And what we found is that this ortho EDDHA iron chelate tends to be maybe the most effective, but also the most consistent at seeing a benefit from the use of that fertilizer. And so this is some pictures from Sarah Lovis as well as Dr. Goose. And it's not just putting some of that fertilizer down, but it's also the concentration of that ortho EDDHA. So this left set of pictures, we have 1.5% of the ortho EDDHA iron chelate. And on the right-hand side, we have 5.5% of the ortho EDDHA iron chelate. So we have our control pots, but then we also have 10 milligrams of the 1.5%, also 10 milligrams of the 5.5%, and 20 milligrams of each concentration. And as you see, that concentration of the 5.5% applied at the same rate, definitely those soybeans look better than that lower rate. So when you're evaluating the different chelates out there, also make sure you know what that concentration is and account for it. Some other ways to help reduce IDC is with the use of companion crops. So the amount of calcium carbonate definitely influences IDC. And really what happens is iron, we have a lot of iron in our soils. The iron soil test isn't really diagnostic, just because it doesn't tell you if that iron, what form the iron is in. Ferrous iron, that's the Fe2, that's gray and black looking, is highly plant available. However, that is most prevalent in the soil under saturated conditions, and most crops don't do well under those reduced conditions or where there's without oxygen for long periods of time. The rust colors you see, that's ferric iron, that's the Fe3. that isn't really plant available. It doesn't dissolve in the soil solution easily. So soybeans, they'll secrete these acids and reducing agents that help convert that ferric iron to the ferrous iron, as well as some chelating agents to help improve that iron uptake. And the IDC tolerant varieties, they're just a little bit better at doing that. Now, IDC can be exacerbated by salinity, moisture, as well as excess nitrogen. As soil nitrogen increases, so does IDC. And companion crops, such as oats or barley, applied at about a bushel an acre, will help take up some of that nitrogen. So that helps with the encourage the nodulation of the plant, of the soybean roots. They're a little bit healthier. But then it can also take up some of that excess soil moisture, which that would put more calcium carbonate into that soil solution and increase the negative impacts that it has on that soybean root, releasing those reducing agents. And so you seed some barley or some oats at a bushel per acre. If you have a really wet spring, you might want to wait till you get to V5. If things are pretty dry, you're going to want to terminate that crop much earlier. But again, that number one way to manage IDC is by planting a tolerant variety. So foliar fertilizers. There's been a lot of work done on this throughout the U.S., including Western North Dakota, Montana. And honestly, seeing responses on foliar fertilizers are mixed at best. Every now and then you do see a little bit of consistency with a positive response from foliar fertilizers, but that's under high yielding conditions, such as areas that are a little bit warmer than us, but also that are on irrigation, so you can guarantee some good moisture rainfall when you're at that R3, R5 growth stage, when that water demand for the soybean really peaks for when it's at the grain filling growth stage. So micronutrients. Malorino back in 2015 did an extensive review of micronutrient research that has been conducted throughout the US, and really there isn't much of a response regardless of where you go for that information. Michigan's a little bit different. They do have well documented, or maybe not well, commonly documented manganese deficiencies in their soils out that way, and that has to deal with the parent materials of the soil. But in most instances, micronutrients, we usually don't see a response from that. Now, I talked a little bit about hemoglobin and nodules earlier. Back in 1959, Ahmed and Evans found that cobalt is an essential nutrient for nodules in order for them to form their hemoglobin compounds. We get cobalt from a B12 vitamin. So some of the research that I've done has looked at cobalt applications on soybeans to see if that improves growth of soybeans. And so this is some cobalt sulfate. I actually found it on Amazon. We applied this at about a pound per acre. And when you look at most of the research that has been done on it, a little goes a long ways. When you usually, at least in the research outside of North Dakota that I've come across, when you're in the parts per billion of concentration, that is adequate. Once you start getting into parts per million, you can actually have a toxic effect from too much cobalt. But again, we never saw a response in our trials in North Dakota. Liming and acidic soils. So soil acidity is starting to become more widespread in North Dakota. We'll focus on here with the nitrogen fertilizer. So you put some urea down, or anhydrous, or even manure. At some point, that's going to nitrify and turn into nitrate, this NO3. And as that fertilizer converts into nitrate, hydrogen is released, and pH is essentially the concentration of hydrogen. So over time, we can acidify our soils, more so in no-till soils, just because we're putting that nitrogen in the same area year after year, so there can be a concentration of acidity wherever that nitrogen is put. So strong acidity can do a handful of things adversely to the soil. One is when the pH starts getting less than 5.5, it can greatly inhibit microbial activity. So you might have some issues with nodulation or other bacteria that are nitrifying or mineralizing other nutrients within the soil. You can also have aluminum toxicity, and we don't worry about that unless our soil pH is less than 5.5. And our clays are predominantly made up of aluminum and silica. So we have a lot of aluminum in the soil, but if your pH is less than 5.5, it's there physically, but it's more so chemically inert. And so when that pH gets less than 5.5, aluminum frees up and it can have this toxic effect with the plant. But also, it can have this snowball effect and acidify the soil even more. So aluminum has a +3 charge. That's a pretty big magnet in the soil, and everything wants to have a net zero charge at the end of it. So aluminum can split this H2O in half, and the OH, or the hydroxyl, binds to it. So the aluminum will split 3 water molecules, but then it'll also release 3 hydrogens, which would increase the acidity and decrease the pH of the soil. So as the aluminum is freed up, it can tie up phosphorus. We see a lot of phosphorus tie up with calcium issues in North Dakota. That's more so with calcium, but we certainly can see that in areas with lower pH, and calcium has a +2 charge. Aluminum has a +3 charge, so aluminum is actually a bigger magnet than the calcium and can tie up that phosphorus even more so than the calcium. So it might at first look like a phosphorus deficiency. So your older leaves, they might get that purple look to it, but the new leaves still look healthy because phosphorus is a plant mobile nutrient. But as it worsens, aluminum can abnormally shape roots, so that's going to hinder the water and nutrient uptake of that plant. And now we've even seen in some instances in North Dakota manganese toxicity in the really acidic soils, like a pH of less than 4.5. We've seen that in a few spots. So this is a picture that Ryan Beto sent me, and this is what aluminum toxicity looks like on our small grains. You can see there's sparse germination, but if you look at these lower areas of the plant, it kind of has that lighter green look. So whereas the upper parts of the plant maybe look okay, so that kind of looks like a nitrogen deficiency to me. So maybe some microbial activity is being hindered under these conditions here. So we've been doing work on liming soils in North Dakota. We've successfully improved soil pH with surface applied lime when we've applied the lime at planting on soybeans, and going back out and soil testing shortly after harvest. We've improved the soil pH from like 5.3 up to about 6.2 with 2 tons of beet lime, but we haven't seen a yield response on that. So we got more work to do to try to figure this liming thing out. But this is an unrelated trial. I just wanted to show in the foreground here, we have 2 tons of lime. In the middle is 8 tons, and this is all beet lime, so there's about 75% calcium carbonate there. And in the background is 4 tons of lime. So we have our treatments here. We have the pH, and you see that the pH, once we put that 2 tons down, we get over that 5.5 pH threshold for aluminum as well as microbial activity. But as we increase our application of lime, that increase of pH kind of plateaus out. And when we think about it, the pH scale is log based. So if you move from a pH of 7 to 6, that is a factor of 10. But if you move from a pH of 7 to 5, there's 100 times more hydrogen in that pH of 5 versus that pH of 6. And so that's why we kind of see this response, at least with the pH, plateau out. But regardless, as we increase that application of lime, the aluminum concentration does decrease. And so we've been doing our work with sugar beet spent lime from Sydney Sugars over in Montana. Last fall, it was $41 a ton delivered to the research center in Minot. And we figured $9 or $10 per acre to have that custom applied on our fields. So in summary, Inoculate if you've had inoculum issues in the past, or if it's virgin soybean ground. Soybeans are really efficient at mining soil phosphorus, so we've changed our thresholds of phosphorus. And also make sure you know where you're at in the state and adjust your potassium recommendations accordingly based on the amount of smectitic clay in your soil. We rarely see benefits from micronutrients, and IDC can certainly be an issue, but again, your number one way to manage that is with an IDC tolerant variety. So I just, another quick thing to keep in mind, I just finished up my PhD where I evaluated 16 different fertilizer treatments over 6 years in Northwest and North Central North Dakota. A couple of the plots were in Minot. I did have one down towards the Garrison Dam, but then I also had 3 other plots over towards the Crosby area. And out of those 16 treatments, not 1 year did I see a benefit from the use of any of those fertilizers. So with that, thank you everybody for your attention. And are there any questions?